All right, hello and welcome to a very fun lecture. I'm super excited to teach this to you. I promise to not test you on these topics, but they're just super fun, and it's a great review of a lot of stuff that we've learned. So without any further ado, let's get into it. Let's talk about reverse engineering and hacking today. So pretty fun concepts, right? Reverse engineering, if you haven't heard that term before, it doesn't mean anything bad, like maybe hacking sometimes means these days. Reverse engineering is just like when you take something apart to see how it works. You can reverse engineer like a physical piece of your car, for example. So it's not really a bad thing. So I'm going to teach you, I guess, both today. And so by the end of this lecture, you will be as capable as this hacker man from this silly YouTube short movie. Okay? So yeah, let's talk about XXD first. All right, it's a terminal program that creates what's called a hex dump of a file, and let me show it to you in terms of a Hello World program. All right, so if you go and look up XXD in the manual, it will tell you that it can take some stuff. You can give it some options. It makes a hex dump, or it runs it in reverse as well. So that's pretty cool. So let me show it to you in terms of a hello C file, so a C program. Standard.io.h, and then we'll printf hello world, and a new line, of course, and then we'll return 0. All right, so we got this program. We can compile it with GCC, of course. There we go. -o hello, and you know better, right? Now that you've taken this class, at least, you know that this hello program, that's our executable file. It is not human readable. You've maybe accidentally done this one day. And it's just disgusting. It's a bunch of unprintable characters, mostly, and this is like the machine code for that program. You can run it, of course, and it works. That the CPU could understand it, but humans can't really understand it. And it's just a bunch of binary stuff. So XXD is all about taking a binary program and emitting something that lets us like understand it better. It creates, it'll turn it into a text-based hexadecimal format. Okay, so yeah, if we run XXD on a program, we can also give a file name, and it will like output the hex dump. If you give this as well, it'll turn off the colors. So you can just say XXD by itself on the executable file, and here's kind of what it looks like. XXD hello. It's very pretty. By default, it has colors these days, which is new, but we want to turn that off when it saves it into a file. You can say XXD, name of the thing you want to create this hex dump of, and then we'll give it a file name called like hello hexdump.txt, but I want to turn off the colors, and so to do that you say like -r, I forget what the R means, but like never output any colors, please. And so yeah, that creates a third file that I can then go and look at. It's the hex dump of the hello program, not just printed to the screen anymore. All right, so here's that. And on the left side, these are like offsets into the file. This is like the first 16 bytes of the file, the next 16 bytes, the third 16 bytes of the file. All right, these are hexadecimal numbers. You see how they're counting up in hex. And these are the hexadecimal bytes of the file, the start of the file. It's like, okay, the first byte in the file is 7F, then it's 45, then it's 4C, then 46. And then over here on the right is if ever those bytes correspond to ASCII code values that are actually printable characters, it'll show you those over here. So like these, the second, third, and fourth bytes in the file spell out ELF, and there's actually a reason for that. That was on purpose. So that's kind of cool to think about. And then some of these other ones just like randomly, okay, that's an @ sign. Cool. The dots just mean it was like unprintable, or like white space. So yeah, some of these things like have words if you scroll down, and so that's what it means to be a hex dump. It's telling you like, okay, this is what the file looks like. Here's its binary form in hexadecimal now. Okay, so yeah, what you can do now is you can make changes to that hex dump file. You can change the bits. You can be like, all right, it's not 38 anymore, it's 39. Like you can do that, and you can resave the file and have XXD run it itself in reverse. Go from the hex dump to a brand new program that you can then go and run after you've changed the bits around, or the bytes. Isn't that cool? So it just like makes it a binary again that you can then go and run. So here's what we'll do. We'll take this hello world program and we'll change the string hello world. All right, because it's sitting there somewhere in the program. It's sitting there in the executable file. It's loading the hello world string from it. So somewhere secretly is this. You got your hello world string somewhere in the program. Hello world, exclamation point. We included a new line, and then it'll be a C string, like \0 for sure. If you look at the disassembly, you'll notice that it's going to get rid of the new line. Or sorry, if you look at the assembly, if you do gcc-s, you'll notice that. But you can just search for hello. There it is. It is at offset 790-ish. Oh, exactly, yeah, 790 in hex. There's the H character, the E, the L, the L, the O. Look at them. There's the space, W-O-R-L, that must be D. There's your exclamation point. And there is no new line. It just goes straight to the null terminator character. So for a reason, it got rid of the new line. It's just like saving space. It doesn't need it after all. And so it just has the null terminator right after. And for some reason, I couldn't delete that, but I guess that's fine. So you got the null terminator right after it. Okay? So let me redraw that though. Oh gosh, why is it not working? So something is, my PowerPoint is unhappy right now for some reason. Hopefully I can still draw new things. We will find out. Looks good enough for me, all right? So what we can do is we can change characters. Like these are bytes, they're being loaded by the program. If this is an H right now, we can make it something other than H. Does that make sense? So like if I change what's here, that's going to change what's printed because it's just going to here in the file, loading the string, being like, okay, print from this address. If I change the string, I can change what gets printed. Isn't that cool? So you can't change what was after. Like this is the null terminator byte of that string. Everything after that is some other piece of the program, and you don't want to mess with that, right? Because then you're like, you could be changing an instruction, you could be changing other pieces of the data section. We can't like make the string longer, but we can change it to be anything. Like these bytes we are allowed to mess with because they were part of the original string. Like that's how much the compiler set aside for that one string. All right, so we can make it shorter if we move where the null terminator goes, or we can keep it the exact same length. All right, those are our options. We cannot make a longer one. So let's change hello comma space world exclamation point to hi CSCI 45. That should be a similar amount. Hi, and then all caps CSCI 45, and then an exclamation point still. And then we got to, just in case we change the length, we got to add in the null terminator after the exclamation point still. Okay, so let's make that happen. Let's change this string. Let's figure out what the hex codes need to be. Sadly, we can't just change it here. Like we're gonna do this eventually, but we can't just change it here. So it's like the E becomes an I. You have to actually go and change the hex stuff in order for it to be really changed when we run it in reverse. Okay, so yeah, this is the H, and then instead of a lowercase e, I want an I. So let's figure out what that is. Let's go and consult the ASCII table. Like sure, this is the table, but there's like a more compact table here, and that's what I'm getting at. Hex and decimal. So this is the one. This is the one I want to use. So okay, so instead of E, I want I, which is here. It is going to be, looks like it's 6 and then 9. 6, 9. All right, so 6, 9 instead of 6, 5. Cool. And then I want a space, which is, it's this one right here. It's the 2, 0 for a space. We can confirm that by scrolling up here. If I just zoom out, this makes it easier for me to see the whole table. So yeah, there is 2, 0 as a space character. So there was the I. Then if I make this 2, 0, this byte, 2, 0, now it's a space. And then I want capital C here. That's going to be 4, 3, apparently. So 4, oops. So this will get replaced with 4, 3. And then I need a capital S. So I think it's still going to be 4 something. In theory. Oh, no, it's not. Never mind. It's going to be 5, right? 5, 3. Right there, 5, 3. So 5, 3. Hi, space, C, S, and then I need another C, so 4, 3 again. And then an I, capital I. And that looks like it'll be down here, GHI. So something ending with 9. going to be 49. 49, and then I want another space, so that was the 20 in hex, and then 45, the characters, right? The actual characters 45, which is going to be 3, 3, 4 for the 4, which is weird to think about, I know. There's high space CSCI space, there's the 4, so it's going to be 3, 4, and then 5 is right after it. It's going to be 3, 5 in hex. 3, 5, and then we want an exclamation point, which was 2, 1, right there. 2, 1. We also had it here, and then yeah, our string's a little bit shorter, so we want it to end here. We don't want to keep the old stuff. This was like the D or something. We want to replace that with the null terminator, so that the string, because it's just going to be given as a starting address, it's like starts here, go and print the string until you see the null terminator, because it's a C string. And yeah, we've changed the hex codes here for that string, and so now it's not hello world anymore. All right, so if I save that, now I can run xxd in reverse. So lowercase r, xxd lowercase r, give it the file, and then give it a new file name, because it will output as that. All right. Dun, dun, dun. So that's going to be xxd in reverse, hello hex dump, and I'll call it, I don't know, hello edited. All right. And no extensions, because this is going to be a runnable thing. I actually need to mark it as runnable, because by default it's just like something that's not able to be run. It has no execute bit set right now, so I'm going to set the execute bit for myself, u plus x, or here we can do it in we'll do an octal, right? So it's going to be 7 if I want to read, write, and execute. 7 and then 0, 0 for everybody else. Hello edited. And so now I just set that x bit. Cool. So now I can run this. My old hello looked like that. My new hello edited. Look at it. That's pretty cool. We changed the string in the binary file. That's pretty amazing. All right. Yeah, so that's what we just did. I think that's pretty cool. All right. So, yeah, that's like reverse engineering, seeing how things are working. Let me next show you like an example of changing the instructions themselves. That'll be cool. So I think I showed you this once upon a time, maybe. There's a program called objdump, and you can say objdump-d. D stands for disassemble. So you can give it a compiled program still, something that's binary, that's runnable by the CPU, and objdump-d spits out what's called disassembly. Disassembly, it goes in reverse. It's like, you know, an assembler takes assembly code and makes a binary file. This goes in reverse. It disassembles. It takes a binary file, creates assembly. So yeah, let's do that for our hello world file. Okay. So I'll say objdump, and I'll go over here. I'll say objdump-d, and we'll do it on the let's see here. We'll do it on the original. Why not? Hello. So if you just press enter, it will like generate all the assembly and just shove it onto the screen. But we can also save that. So go out here to well, what's a good file name? I'll call it hello disassembly.txt, and then you can look at it. All right. So vim hello disassembly.txt. And like then you can eventually find the main function, and you can kind of see why. Where's the main label? There it was. Here it is. You can see kind of why it was why it got rid of actually that new line, because we had that. We had that in the C file. It got rid of this. It got rid of the new line in, if you remember from the hex dump file. The reason is because it changed printf to a call to puts. Put s for put a string onto the screen, and this library function by default adds a new line for you, and so that's interesting. So it changed, the compiler changed printf into puts, and yeah, this is us looking at the binary and figuring out what were the assembly things that corresponded to to this program? What were the assembly instructions? So yeah, that's what objdump-d does for you. Also, before I forget, we can confirm, right, that our hello edited file, like it has that new string in the new position. We can do our xxd-r never give the hello edited file, and we'll call it hello edited hex dump. And so there it is. Hi, CSCI 45, and then had the remainder from the other string. Remember that? It was like just an extra. There was our null terminator that we added, and then we had another exclamation point from the other string, and then also a null terminator. So yeah, our string stops there, but yeah, there was extra stuff because we overwrote. That's what we had to do. We can't add things, can't remove things. We can only overwrite in these files because that changes offsets for everybody, right? So yeah, that's what that's xxd again, and then objdump gives you the assembly. And if you look at it closely, if we go back to it, hello, not hex dump, but disassembly. Go back to the main function. You'll see like here are some commands, like instructions, and then over here, like these are offsets into the file, just like xxd was doing. And then it's also giving you the hex form of that actual instruction. Interesting. So let's look at that. All right. So this is the offset, and then it gives you the binary code for this instruction, whatever it was. Isn't that interesting? So now when you do xxd, like you can look this up. You can go to like, okay, go to offset 750, find, and then like go 8 bytes over to where it begins, and like you see this thing that it told you. You see it in the file. You see it in little endian though. Okay. So let's prove that to ourselves. Here's the, for example, here is the call to the printing function, the puts that, or puts that our printf got transformed into. Let's go and look at the hello hex dump.txt file, and we don't care about this anymore, but let's go and find 764. Where's that? It's up here. Cool. So there it is, 76. This is 760, 761, 762, 763, 764. So that's where it starts. And every instruction in our 64-bit ARM processor is going to be 4 bytes long, 32 bits. And so here is that same instruction, but it's stored in little endian. So it is really 97FFFFB3, but we're storing it in little endian. So it's 97FFFFB3. So those are the instructions themselves. Of course, that's there in the binary, but maybe you never thought about it that way. That's pretty cool. So just like we can change strings just by changing hex values, we can change instructions too by changing hex values if we know where they are. Now that's very powerful. That leads to us being able to hack things. Okay, so yeah, here's our goal. All right, let's make a password protected program that we'll use string compare because it's easier. We'll use the C library rather than the C++ library because things get really disgusting with the name mangling. And we're going to hack the program, even though we're going to put the password in the program as we write it. We'll pretend it was somebody else's. And we'll have it let us in no matter what password we use. So we'll hack it to maybe find the password first, and then we'll also change it so that it lets everybody in always. All right, so we're going to edit the compiled binary file for this password protected program. That'll be really cool. Okay, so let's make that happen. So I will make a brand new, oops, I just want to quit that. I'll make a brand new C file. Stop that. There we go. What will I call it? I guess I'll say password protected. It'll just be a C program. And then let's look at it. I need string.h for string comparisons. And here will be the program. Let's just make a silly program that will eventually hack. Let's ask the user for a password. Ask for a password. And then we'll use printf for that. Enter the password. And then we need to read in their password, or their guess of the password. Okay, so that'll be a scanf call. We'll say scanf. And it'll be %s because we want to get a string from the user. And we need to read it into somewhere. So we need some memory that will hold strings. So let's make an array of characters. So let's make char user input. You have to upfront kind of say how big, how much stuff you want to get potentially. So let's say that the user will never type more than like 99 characters because we need one more for the null terminator. So let's call it that. User input size 100, string to fill in with the user's password, just space for a string. And then I'll give the address of that start of that string, which is just the name of the that array. Okay, so there it is. I got a string from the user now with scanf, and now let's just compare it to some hard-coded password. Compare it with the real password. So let's be like if string compare the user input, compare that with the secret password, which will be like I love CSCI45. That will be our secret password, okay? And we want it to be equal. So string compare returns 0 if the strings are equal. So we would like that to be the 0 there. And if so, you can imagine this could be like a complicated program that like lets you use your bank account or something, but we'll just print out like print password correct or access denied. Alright, so there's that one. And then otherwise, if they got it wrong, it wasn't equal, then we'll say access denied. So that's kind of cool still. Alright, so there's my program. It's simple, but it'll be a good way of explaining this stuff. Alright, so there it is. Of course, we have it hard-coded. We wrote the program, so we know what the password is. But imagine you were just given the binary. You were not given the, you're not given the actual program itself. Like, you'll just start guessing passwords. Access denied. It's always access denied unless you type the exact right password. I love CSCI45. Yeah, only then is it correct. And like, how are you going to guess that? So here, now we can look into things. We can create a disassembly and like try and understand this program. That's what reverse engineering is all about. We want to understand the program. So yeah, there's a couple things we can do. So let's do objdump on it to see, like, again, pretend we were only given the binary. We were not given the C file. We're only given this binary because that's what programs work like in real life, right? You're like, you buy PowerPoint or something. Nobody's giving you the source code for PowerPoint, but I guess you can reverse engineer it if you wanted to. So I'm gonna say objdump -d on password protected. It spits it all out to the screen. I just want to save it in a file, so I'll call it password protected disassembly.txt. It's a human readable text file. And so now let's look into it. All right, vim password protected disassembly. Let's go to the main function and we'll find the main label. And there's a couple things you can do. You can use the disassembly to find the password first of all. Like, you don't have to actually edit the file. You can just look into it, look at the decompilation. So this time it kept the printf, which is interesting. So that's fun to think about because we didn't have a new line on that first thing. So yeah, it's again great practice to like compare the actual source code with the disassembly. This is what the compiler chose to do here. So you can see it like printing stuff, printf asks for the password, and you can see it also go looking for those strings. Like, you can see where the strings are to, it's using a command that I haven't really told you, adrp, and then it's like doing an offset. So it's trying to find the string in a weird way. And it looks like it's like at offset like 9E0, because it started with 0, I do believe. So let's go and confirm that, because we can go and look at the hex dump of that file, going looking for that string. Like, does it really start there? Was that our enter the password string? We might as well look into that. So here, let's go do that. Let's do an xxd rnever on password protected. And then we'll call it password protected hex dump.txt. And so there we've got the hex dump file now too. It's a lot of things at once. Let's zoom out And look at that one. There it is. And in theory, if my hunch is right, if I go to 9E0 down here, there's the 1s, 3, 4, 5, 6, 7, 8, there's 9E. Ooh, there it is. Yeah, so there's the enter the password string. So you can like use this plus the disassembly to like get at what string it's printing, because like the string's not going to be included here. It's part of the data section. So cool, we found what string it's printing, and then it's calling printf on that. Like we're reverse engineering right now. Isn't that cool? So we're getting there. You can see it making space in memory. Like it's doing a big subtraction from SP. So it's making space on the stack for that string. It's calling scanf eventually. Where's that? There's the scanf call with both the format string as well as a place on the stack, right? A place on the stack to store that string. That's where it placed this user input thing. And so you can see 9F8 apparently. 9F0, so 0, 1, 2, 3, 4, 5, 6, 7, 8. That's where it starts. And there you can see it's just the string %s. Cool. And then of course the null terminator. So yeah, there's that string. We're giving that to scanf. So we can walk through the program. We can recreate essentially the C file if we didn't have it, right? And that's the goal of reverse engineering. Okay. And so like, okay, we got a string back. It was placed in, it was placed on the stack. We can see that happening here. And then again, we're going places. We're going places, and it looks like we're about to call string compare. That seems interesting to our hacker brain. What's going on with string compare? Well, looks like we're going and we're looking for a string offset at A00. So that's this one. And I'm calling that with something that was on the stack, which was that string that I just typed. So if you're a hacker or reverse engineer, this should like make alarm bells go off. Like, ooh, I'm comparing that string to something, that string that I just typed, to something that's in the file itself. Ooh, that's hard-coded something. And then if you go to actually A00, you see like, oh, there's the password, null terminator, because it's a C string. There's the actual password. So you can go and find that, like, oh, I understand that must be the password now. But if you didn't, you can keep reading, right? Okay, what's it doing with string compare? It's comparing it with 0, like making sure, hey, was it 0? If it's not equal, you see how it's doing the opposite as well. If it's not equal to, go to 980, which is this one. That's going to be your access denied case. Like, okay, what happens? BL A28, there's A20, like, yeah, there's the access denied string. Otherwise, if it was actually equal, what are we doing? We're printing with a new line, so puts the string at offset A10, which is password correct. Ooh, all right, so we want to get here. We want to get to this one, okay? So that's our goal. We would like to get to this branch right here. Do you see it? It is everything, yeah, this is the branch. This is the true branch. I hope that makes sense. So, like, we'd like to always get to here and print, like, access granted. We want to always get here. Wouldn't that be nice? All right? That'd be cool. And so we just did the actual reverse engineer. We know the actual password now. So like you can go and be like, oh yeah, I just discovered the password. I don't have to guess it anymore. And that will let you in. That's one way to do it. Or I can show you one last thing, and we will edit the compiled binary to make sure it always lets us in, no matter what password we use. Okay? Does that make sense? That's what we're about to do. So what controlled, right? What instruction controlled whether or not we got to this branch or to the other one, which was this guy right here that's always printing access denied, right? So what controlled one or the other was this comparison in the branch, right? So this branch right here, BNE, like that forced us to go somewhere else if it wasn't 0, if the strings did not compare properly, okay? So what we'd like is we'd like this instruction to always let us through. Let us always go here. Let it always be true, right? So we'd like, there's two things you could do. Like you could change this to be like move 0 into W0, like make sure it's 0. Or you can just make sure that this branch just does nothing. It always falls through, all right? We'd like this to do nothing. That would be nice. do nothing, just fall through. And there's an instruction you can think about, like what kind of instruction could I replace this with that just makes this do nothing at all, essentially. And just like immediately, like don't change any registers or anything, just like keep everything the same, just like spend one clock cycle doing nothing, and then we'll be in the true branch and we're good to go. So like what could we do there? And so the goal is to introduce a what's called a no-op instruction, N-O-P. You might see that. Like that's the name of an instruction in Intel assembly, actually, but we can make our own. We'd like to make an instruction that's a no-op. All right, that's short for no operation. No-op is short for no operation. We'd like to replace that existing instruction that actually did a branch with a no-op, one that actually doesn't do anything at all. So an instruction that keeps everything else the same, but like doesn't do anything. All right, so that's the goal. Alternatively, you can change your BNE maybe to like a BEQ. That's another option. Like you can just make it like when the password is incorrect, like pretend that that's what we wanted. Okay, that's kind of the goal. That's another thing you could do. But let's see here. Yeah, that's one way to do it, but I'd prefer this way. Then it will always let us through. So like what's a good instruction that won't change the values of any registers, but just like does nothing? All right. If you think long enough, this will do that. This is a good example of a no-op. Just like add, I don't know, x0, x0, 0. Do you see how this instruction right here does nothing at all? It keeps x0 whatever it used to be. It adds nothing to it, but it takes up 32 bits. It's a legitimate instruction that will do nothing. So if I were to replace this branch, this BNE, with my no operation, my no-op, my add x0, x0, nothing, then it would always fall through because it's not even using this comparison. Does that make sense? So I'd like to replace this instruction, these 32 bits, with something else, with this thing. All right. So we have to figure out what are the bytes of this. Let's encode this in a certain way. So let's make a Scratch program. Let's make a Scratch program to go and see like what's the binary equivalent of this instruction. All right. Let us figure it out together. So yeah, let's make a Scratch program now. I will make a new file just called like scratch.s, but honestly I need something that is going to be easy. So let me steal lecture 1 something, like just like a return from main, like return an assembly file. Let's steal that and let's copy it in here. Copy lecture 1's return in assembly.s, so I can just add to it, and I'll call it scratch. Scratch.s. All right, so now I've got a scratch.s file, and this was everything that we learned on the first day of class. Let's add in, right, our one thing that we care about knowing what it was. So like add x0, x0, 0, right? That's my no operation, my no-op. This instruction does nothing. It just like heats up the computer some more. Does nothing of value. Okay, so that's exactly what we need right here. We just want to pause and not do what we usually did. So let me just assemble this. As scratch.s-o scratch.o, because all I need to do is like I don't need to execute this. I don't need to run this file. I just need to look at its disassembly. So I'll say objdump -d scratch.o, and then like that's useful, but I'll save it so that you can see it later too. Scratch disassembly.txt, and yeah, looking at it, we see that apparently the 32 bits that correspond to that exact add instruction are 9, 1, and then a bunch of zeros. Okay, so we're gonna have to store that inside of our inside of the line that we care about changing. Okay, that's what we would like. That's the binary equivalent of this instruction. I'd like to replace that BNE with this. All right. Remember that it's got to be as a little endian thing though. Okay, so let's go back. Let's go back to everything. So where was I? We got a lot of things to open or not open. So I need this. I need the disassembly, right? This is the. Where's the line that I'd like to change? This one. I'd like to make sure that this line gets changed to something else. So it was 96C. I want to replace it. All right, I want to replace my 96C with scratch disassembly. I'd like to replace it with this one. So it used to be this 5-4, a bunch of zeros, A1. I want to replace it with 9-1 and then some zeros. All right, that's the exchange that needs to take place here. Okay, because that's what I'd like to do. All right, I'd like that to always follow through. So I'd like to turn this into a no operation, a no op, by replacing this. So okay, I know where that lives. I have my hex dump, password protected hex dump file. Okay, we're almost home free. So I want to go to 96C. 96C is where this instruction lives. I want to change those 4 bytes. So let me scroll down to 96C. Whee. So the best I can get to is 96, then I have to offset. So 960, 961, 962, 3, 4, 5, 6, 7, 8, 9, A, B, C. There it is. And you see how it's stored in little endian. So it's not 540000A1, it's A1000054. Little endian, all right? So this I need to replace. This I need to replace with this. All right, remember still it's little endian. So like this guy's going first. It's a bunch of zeros, 0 bytes, and then a 9-1, all right? So it's a bunch of zeros, or keep those zeros, we're good. And then it's gonna be 9-1, all right? And that will change it into the way that we wanted it to be, okay? So that should do it, and I believe we are home free now. I think we've done it. So let's run our hex dump in reverse now. All right, so I'm gonna say xxt-r password protected hex dump, and I'll call it password protected hacked. All right. And so it spit out this file, password protected hacked. It's not runnable yet, so I'll chmod it to mark it as, yeah, that's a binary thing I want to run actually. Password protected hacked. Boop. So now it's green, I can run it. And so without any further ado, watch. So my old password protected program was like, you type anything that wasn't the password, it's access denied. But password protected hacked, we have gotten rid of this check. We've changed it into a no op. So now, no matter what password I type, it's always going to give me the access. It's always going to grant me access, even if I type the normal one. We've just like gotten rid of the check. So nothing is wrong anymore. Everything is correct. Every password. That's pretty cool. And so let's confirm that. Let's go and disassemble now. Let's come full circle. Let's take our hacked program, disassemble it. All right. So objdump-d password protected hacked. And I want to send it to a place called password protected hacked. These are getting very long names, aren't they? Hacked disassembly. .txt. Disgustingly long. But let's look at it. Password protected disassembly.txt. Let's go to 970-ish. It was here, 96C. Dun, dun, dun. Oh, sorry. It needed to be password protected hacked disassembly. And we'll go to 96C. 96C. If I type it in the right order and I type the right characters. I'm just too excited. So you see how now this instruction, after the compare, it is no longer what it used to be. It is now my no op. It's my add x0 number 0. Okay? Beautiful. We did it. We did it. We have made it so that this line does nothing at all. That's just like not changing any registers. It's just moving along. And we get to the branch that we care about, no matter what we typed. And that, my friends, is reverse engineering enough to understand the program and hacking it to change it in the way that, like, to get the effect that we like. Okay, so yeah, I think that's what I wanted to show you. I think that's everything. There are other ways around it, though. There's other ways to do this. This is like the simplest way that I could think of, like getting rid of this check. You have other options, right? As a reverse engineer or as a hacker, you could change this comparison to compare against, I think it's like, I guess, no, that would be hard because like the comparison result, string compare can return some arbitrary negative or positive number. So like this comparison is not really the easiest one to change. You could maybe make sure it's 0, like change the string compare call to like move 0 into W0 so that it always is correct. Always was 0. That's one way to do it. Change this to move. Another option, change this to like a move W0, 0. That would work because then it's always going to compare properly. You don't have to change this. Or another option would be to change the BNE. So alternatively, change BNE to be like EQ. So like whenever it's, let's see. So that means it would jump to the true branch, it would fall through unless you got the password right. So every time you got it wrong, it would fall through. Essentially, you've changed the branch to flip-flop it. That's another way to do it. Then all incorrect passwords would be correct. But the correct password then becomes incorrect. So that's something to worry about, maybe. So you have many options. That was one, and yeah, I walked you through how to do it. A great way to practice would be like try one of these other options yourself. All right, I'm giving you all this code. Make it happen. So yeah, that's a silly example. It kind of like goes over a lot of stuff. Like we're remembering like how everything's being, at the end of the day, it's all being translated into binary, and we can change those things. So yeah, hopefully now you feel like HackerMan. I think it is a very fun topic to teach. I hope you enjoyed this lecture. I'm not going to test you on this, but I think you learned a little bit still as you watched it. That will help you on the final and in your future. So yeah, that was fun for me, and I will see you later.